Okay, so this is my Module 3 presentation on the general linear model. So let's talk about the general linear model. First of all, it's important to know that it generalizes to multiple more specific models, and also it's linear, which means it's additive. So we have these logical ORs. So this equation would read much like y is a function of the intercept or the predictor or the error. So more specifically, we have part of this model, we have y, which is the observed data, so what we're interested in understanding and predicting. We have b naught, which is the y-intercept in y units, which is our best guess when there's no predictor present. Then we have this b times x, which is the b part of that is weights we assign to each predictor based on relevance, telling us how much each predictor helps us understand y. It's in rise over run units, so both the units of the predictor and the outcome. And then also just that x is basically representative of a set of variables we can use to make predictions about the dependent variable y. And then we have this e term, this error term. So in MRC, we refer to this as residual. In ANOVA, it's error, and it's expressed in terms of y units. So we essentially have this observed equals predicted plus residual, and that predicted part we refer to as y hat, and that's b naught plus b times x, the observations we would expect given a model. So the GLM encompasses both MRC and ANOVA, and why do we care about this? So MRC is a measure of association that allows us to understand an outcome variable through various predictors, while ANOVA is a measure of difference, which allows us to evaluate differences between group means. And so some important differences to note are, first of all, about the types of variables each works with. So ANOVA mostly deals with categorical class level predictors, variables that need to have these a priori comparisons built in, while MRC mostly deals with covariates. And then MRC is also a little bit more flexible than ANOVA, and this is important because it can handle things like multicollinearity, which we'll talk about later, while ANOVA has these really rigid requirements. So if you violate something like equal cell sizes or independent factors, that renders the results of ANOVA essentially uninterpretable. And finally, they both work under different philosophies. So MRC works under this philosophy of Aristotelian nominalism. So that means that they think that the deviations are interesting. So they look at residuals as resulting from an incomplete model, so errors attributed to the model, while ANOVA works under Platonic essentialism, which basically just thinks of errors as imperfect representations. So they attribute any errors to the observations. And so we're first going to talk about the outcomes associated with MRC. So in MRC, parameter estimation follows this algorithm called ordinary least squares. And this produces the smallest squared deviation. So that deviation is y minus y hat. And the goal is to minimize the total error in our prediction. So we use regression to provide us with a line of best fit that would have the least amount of error. So we're estimating two parameters, the slope and the intercept. And the null hypothesis would be that these two population parameters are equal. And so we use regression to estimate our outcome variable of interest. And so first we're given this r squared value, which basically tells us that 34% of the variance in the outcome variable can be attributed to our model. So it basically tells us how well our model performed, a ratio of how much we explained to how much is still left to explain as far as the outcome variable. And then down here, we have standard errors and B's. So we have standard error. In order to compute a t-test or an f-test, you need to estimate standard error. And so if you remember about standard error, the standard error of B would be the uncertainty we have about a parameter estimate. So a t-value is essentially a ratio of signal to noise. So it's the estimate over the standard error. And as you can see, each t-value is associated with a probability, and none of these reach significance at the 0.05 level. And so we also have these betas, which are standardized coefficients, and essentially those are more helpful because they are range from -1 to 1 and basically allow us to compare relationships between x1 in the outcome variable, x2 in the outcome variable, and x3 in the outcome variable to each other, while these b's are just in rise over run units. However, so a lot of people like to use these betas, but we learned from the King reading that standardized coefficients are in general more difficult to interpret, don't add information that can help us compare the effects really, and also may add misleading information. So he really argues for the use of these original unstandardized coefficients because he thinks that they're more meaningful and not subject to these problems, even though you can't compare effects between x1, x2, and x3, he finds them more useful. So given that none of our effects reach significance, we want to know what might have gone wrong. And so we're going to look at some diagnostics. And so MRC and ANOVA follow various assumptions, and violations of these assumptions can be affecting our results, which prevent us from understanding the effectiveness of our models. So the first one I want to look at is multicollinearity, and this just refers to when we have predictors that are correlated. And so correlations among predictors interferes with our ability to assign causal priority. So when we run these tests, there's a partitioning of variance that occurs, and that occurs through sums of squares. And so ANOVA uses type 3 sums of squares, which is just simultaneous sums of squares. So it's the most conservative approach, and various estimates for each predictor are adjusted for all other effects of the model. You could also maybe use type 1 sums of squares because that allows for hierarchical partitioning of variance, but we're kind of stuck with what ANOVA does. And so variables may share variance that is not relevant to the outcome variable, and that is what produces those collinear relationships. And this collinearity inflates type 2 error because undetected effects are never evaluated, and as we know, that's a really horrible thing. So we're looking here at this plot of the correlations between our predictors, and we can also look at standard error and VIF. So the relationship between multicollinearity and standard error is that as collinearity increases, so does standard error. And so large standard errors means we would have a lower likelihood of making accurate predictions and a lower likelihood of rejecting the null, even if the null is false. So we're looking that large standard errors will be bad and reduce our likelihood of reaching significance. And then we also have this VIF factor, which is a collinearity statistic. And this really is dependent on this R squared sub J term, which is the multiple coefficient of determination. And that just tells us the amount of shared variance between the predictors. So a multiple R squared term means we have increased variance inflation. And so basically anything over 1, given that these are pretty close to 1, you might not think it's an issue, but one of our factors is pretty close to significance. So it's important to look if these do deviate from, if they are greater than 1, how that might be affecting your relationships, and maybe looking at those relationships independently. And so now we're going to check for influential outliers. So it's always really important to plot your data because you need to check that X and Y follow this rectilinear relationship. So I just have the outcome variable plotted with all 3 predictors here. And we're looking to see if there are any outliers. And so basically some researchers like to just throw away outliers right off the bat. So but the Cortina, what we learned from the Cortina reading is that there are different kinds of outliers. So the appropriateness of removing these outliers like that would just vary across different situations. So he suggests that we come up with an agreed upon guideline for dealing with outliers that takes into account the causes and effects of outliers. So essentially we're looking visually here for outliers, and then we want to know how influential they might be. So one way we can do that is looking at leverage. And so leverage is the extent to which any single observation influences predicted values. And so I have this centered leverage value here, and what you can do is look at the mean centered leverage value. And any Y value that would have a leverage value that's greater than 2 times the mean might be overly influential. So essentially you can go back and look through and then eliminate any of those values and run your model again. And so we can also look at influence through the scale location plot. And this is a plot of leverage to residuals. And basically, the important part about this is that it takes into account leverage and discrepancy. So, and leverage times discrepancy is equal to influence. And so our measure of influence is Cook's distance. And this is useful in determining if values with high leverage are discrepant. And so discrepancy just looks to identify values that fall outside of an expected range. So the more discrepant an observation is, the more likely that it may adversely impact our results. And so now we can look at our residuals. And so another important assumption of MRC is normally distributed residuals that are centered at 0. So as you can see from this histogram, we can pretty much see that they're right around 0 and that they're relatively normally distributed. We have this normal distribution curve, and the PP plot also tells us that similarly, that our data points are falling right among this line, which means that they're relatively normally distributed. And finally, we need our residuals to not be predicted, and that means homoscedasticity. So this plot is the unstandardized predicted value and the standardized residual. So we don't want our residuals to vary systematically, so a violation of this would be heteroscedasticity, and that would mean that there was a relationship between the predicted Y values and the residuals. But we can see from this plot that we're looking pretty good in that sense. So we might have problems with collinearity and maybe outliers, but not so much with any of our residuals. So before we get into ANOVA, I think it's really important to kind of focus on what we need to pull from MRC that's still relevant in the larger GLM. So first of all, we're still explaining variance in an outcome variable with ANOVA as we are in MRC. We're trying to reduce our uncertainty. And also we have these similar assumptions, most of them dealing with what I just talked about. So independent, identically distributed errors and that are normally distributed. And then also we have this point by serial correlation, and this really drives home the idea that both MRC and ANOVA fall under the GLM because it acts as the bridge between the two. And the point by serial is a correlation between a binary and a continuous variable. And basically you can convert T's and Pearson R correlations between one another. So these tests are super interrelated. So now getting into the parameter estimation and hypothesis testing of ANOVA outcomes. So basically ANOVA is a lot of mean comparisons as opposed to just two means. And so to evaluate ANOVA, we use an F test, which is a test of variances that represents signal to noise ratio. And this can be extended to multiple level factors. So to compute an F, we use mean squares, which is just another way of saying variance. And every F value given degrees of freedom is associated with a probability. And we use this p-value to assess whether or not we can reject the null hypothesis. So as you can see over here, we unfortunately don't have any significance with either of our factors or the interaction term. And this was an omnibus test. So these factors only have two levels, but when you have more than two levels, basically you need to do a post hoc test because your omnibus hypothesis test, significance test tells us if your groups differ, but not how they differ. So you would need to do a post hoc test to evaluate specifically how they differ. And so given that we didn't reach significance, we want to make sure our results are interpretable. And so to do that, we have to make sure we don't have confounded variables. So before I ran the test, I did look at the relationship between the factors in F1 and F5 do have a correlation of 0. So we can say that they're independent factors. So that's good. So now we should look at some other diagnostics to see what might be going on in our test. And so the biggest problem here is going to be equal cell sizes. So as you can see from looking at this between subject factors and the descriptive statistics, it gives us the group sizes over here. We don't have equal cell sizes, and that makes it really hard for us to reach the IID assumptions, independent, identically distributed, and normally distributed. So essentially, we need equal variances between groups, and to get that, we need the membership in the classes to be equal. So we assume they're identically distributed because we require the same number of subjects in each group. So we can't really say that we have that when we have these unequal cell sizes. But there is a significance test for this homogeneity of error variance. So we can look at that through the Levene's test, which there's it's greater than 0.05. So we do fail to reject the null hypothesis, which is good because we can then assume to some degree that our errors are homogeneous. And we can also do a significance test for the distribution of errors being normal. And this is the Kolmogorov-Smirnov test. And again, as with the Levene's test, we did not reach significance, so we failed to reject the null, which means we can assume that our errors are normally distributed. And then also we can check for homoscedasticity, similarly to how we checked in ANOVA, by this plot of our predictive to our standardized residuals. And it looks a little bit different because we are looking at the homoscedasticity by group, but essentially it's the same idea where you're looking for them to not be able to be predicted. And so this plot looks like relatively good, but also it's rather arbitrary to look by each group to see that kind of distribution. So essentially our biggest problem with this ANOVA test was that equal cell sizes. And so what did we really learn? So these assumptions are only important insofar as people actually use them. So a lot of researchers will say that their models are robust to violations of the assumptions. So they fail to look at the assumptions more closely because they think that a lot of the assumptions don't necessarily have a huge effect. But that doesn't mean that there aren't going to be cases where they are having a huge effect. So as we did learn from King, we need to concentrate on having interpretable statistics. So if the statistics are complicated, it's okay, but they need to be able to be meaningful and interpretable. And we really need to understand these assumptions so that we can interpret the results of MRC and ANOVA. And here are my hand calculations.